All right, welcome. Today, we're going to pull back the curtain on our modern world. We're going to uncover this hidden mathematical code that, believe it or not, secretly runs pretty much everything you do online, from your bank account all the way to your social feed. So let's dive right in.
Okay, so look at this. On one side, you've got the wild, totally unpredictable swings of the financial markets. It looks like pure chaos, right? But then on the other side, you have this perfectly structured, orderly analysis of something that's just as complex, the Bitcoin blockchain. It feels like a total contradiction. So how on earth do we find such clear order inside these massive, complicated systems?
Well, that brings us to our big question. What is this invisible engine? It's a special kind of mathematics that deals not with smooth, continuous lines, but with distinct, separate steps. It's called discrete mathematics, and it is the secret architect of our entire digital age. So, first up, let's start by mapping out our digital universe. You're about to see how the exact same mathematics that traces cryptocurrency transactions is also what helps you figure out your daily commute.
This incredibly powerful tool is called graph theory. Now, don't let the name intimidate you. At its heart, it's really just about connecting dots with lines. Seriously. The dots can be anything. People, bank accounts, locations on a map, and the lines just show how they're all related. It is the perfect way to visualize and make sense of complex networks.
And here is graph theory in action. Researchers use frameworks just like this one to analyze the entire public Bitcoin ledger. Every single transaction becomes a part of this massive interconnected web, which lets them, follow the money and actually understand the flow of the entire ecosystem.
And what can they find with this? Oh, a lot. They can identify the major players in the network, the big whales. They can track the path of coins from one wallet to another, which is absolutely crucial for law enforcement. They can even detect these little communities of related users to spot things like fraud and money laundering.
But here's the amazing part. This really complex analysis uses the same foundational math that powers the map on your phone. Yeah, when your navigation app finds the quickest route, it's solving what's called a shortest path problem on a graph. The key takeaway here is this. The same logic that tracks crypto funds is also what gets you to your friend's house on time. Okay, so if we can map existing networks, can we also use discrete math to maybe chart a course into the future? Let's take a look at that in the volatile world of finance and see if we can actually predict market movements. First, a really key distinction. Discrete math deals with countable steps. Just think of a digital clock, jumping from, say, 1057 to 1058. There's nothing in between. Continuous math, on the other hand, is like an old-school analog clock, where the second hand just sweeps smoothly through every single instant. Financial models often simplify reality by treating time in these discrete step-by-step chunks.
A perfect illustration of this is the binomial tree model. It simplifies the future by assuming a stock that's at $20 right now can only move to one of two values in the next step, maybe up to $22 or down to $18. By building out a whole tree of these possibilities, analysts can actually calculate the value of really complex financial options.
And we can take this even further with something called a hidden Markov model. It's pretty cool. This model tries to predict stock prices by assuming the market is always in some kind of hidden state, like a bull market or a bear market. By analyzing historical data, it learns the probability of switching between these states, and it uses that to forecast where prices might go next.
Okay, for our final topic, let's enter the world of secrets and cryptography. This is where discrete math really acts as the guardian of our digital lives, and it leads to one of the most mind-bending ideas in all of computer science. Let's start with a question you've probably wondered about yourself. How many different combinations are there for just a basic 8-character password? Well, the answer is enormous. And figuring that out is a classic problem in an area called combinatorics, which is basically the mathematics of counting. This right here is the first line of defense for all of your accounts.
And this same mathematical foundation is exactly what allows your messaging and banking apps to work securely. It powers the encryption that scrambles your private information into what looks like total gibberish, which can only be unlocked by the one person who holds the secret key.
But what if you need to prove you know a secret without actually revealing the secret itself? I know, it sounds impossible, but this is the revolutionary idea behind something called zero-knowledge proofs. Just like the name says, you prove your knowledge, but the other person learns, well, zero new information, other than the fact that your claim is true.
My absolute favorite way to understand this is the Where's Wally analogy. So imagine you want to prove to a friend you found Wally, but you refuse to tell them where he is. Instead, you take this huge piece of cardboard, you cut a tiny, Wally-sized hole in it, and you place it over the page so only Wally is visible through the hole. Now, your friend is 100% convinced you found him, but they have learned absolutely nothing about his location on the page. That, in a nutshell, is a zero-knowledge proof.
Now, for these proofs to be mathematically sound, they need to have 3 key properties. First, completeness. If you actually know the secret, you can always pass the test. Second, soundness. If you're lying, you can't fool the verifier. And third, the zero-knowledge property. The verifier learns nothing except that, yes, your claim is true.
So let's bring this all together. From mapping our networks to trying to predict the future and guarding our deepest secrets, discrete mathematics is truly the invisible bedrock of our modern world.
So, the invisible engine is finally revealed. We've seen how graph theory maps our complex systems, we've seen how discrete models help us navigate financial uncertainty, and of course, how cryptography builds the walls that protect our digital identity.
And you know, this idea has been revolutionary for decades. This quote here from the pioneers of zero-knowledge proofs back in 1989, it just captures the spirit of it all perfectly. It highlights a huge shift in how we think about knowledge and security. By being smarter about how we prove things, we can actually communicate less information, not more.
This is the invisible engine that makes our interconnected world possible. So the next time you use your phone's navigation or check your bank balance or send a secure message, you'll know about the elegant, discrete mathematics working silently behind the scenes. Which leaves us with one last thought. We've seen the math of today. What invisible math will build the world of tomorrow?